Alright, so with this video, I wanted to kind of list down a number of rules or tips and tricks and things like that to remember when you're dealing with Feynman diagrams, because obviously there's an infinite number of Feynman diagrams you can draw, but there's not that many rules about them. There's actually just a few rules, and as long as you follow those rules, then the diagrams you would be drawing will be for allowed interactions. Because of course we could draw anything we want. It doesn't mean it's something that could actually happen in this universe. So we just want to make sure that when we do draw a Feynman diagram, or when we look at a Feynman diagram someone gives us, we can tell whether it's a true one, an allowed one, or whether it's nonsense. So first thing to note, of course, when we did the Feynman diagram video last time, we went through it a little bit, but just to go through everything from the beginning, fermions, that is the particles, not the forces, not the force particles, but the actual matter particle stuff, are given by a line, a solid line, that goes to a vertex, and if the arrow points towards the vertex, that is a fermion. Incoming, that is going towards the vertex. Whereas if we have from a vertex the arrows pointing away, this would be a fermion outgoing, leaving the vertex. Okay, makes sense. We're coming in or we're going out. However, we also know there exists antimatter, and so the rule is the opposite for anti-fermions. So for a positron or an antiproton or whatever, if you have an anti-fermion coming in, the arrow points away from the vertex. So this is anti-fermion incoming. It's weird because it shows it going away, but this is just a convention, and it helps get all the stuff correct when we do the math. An outgoing antifermion, again, points in the opposite direction from what you'd think. So antifermion outgoing. Okay. Then, so those are the fermions. That's all you can do with fermions. They're either coming in or they're going out. That's it. The other types of particles are the bosons. These are the things that allow for the interactions. They're sometimes, we could call them propagators in certain circumstances, or mediators in other circumstances. But the rules that I'll follow here are that photons will be drawn like this, if I can help it. Gamma. That's a photon. The W's and Z's, the weak interaction particles, I'll draw with dashed lines. So this is either W plus or W minus or Z. And then the gluon, it looks like a little spring. Little G, that's the gluon. So these are the weak scalar and vector, or scalar bosons and things. All right, so those are the different lines we may be drawing on a particular vertex, something like this. We've got the fermions, they're the solid lines. Photons are the wavy lines. I do the weak bosons as dashed, and the gluons are spirally. Sometimes the other convention is that the weak bosons are drawn just like photons. It's just instead of putting a gamma, you put a W, right? But I like to kind of differentiate it just so it's evident right from the start, is this a weak interaction or an electromagnetic interaction? All right, so what are some of the allowable vertices that can happen? Well, one thing you can do is you could put three lines together, and in fact every vertex is going to be made of three. Sometimes you can have four, but the majority of them are going to have three. And we could have something like this. We could have a fermion coming in, and then here's a photon, and here's a fermion. So we'll have incoming, and this could be, if this is a photon interaction here, this could be either leptons or quarks, and when I say leptons, I'm excluding the neutrinos. So this could be electrons, muons, tau, or quarks. So I'll put L for leptons or quarks. And the what kind of thing is that? And also, by the way, if a lepton is coming in, the same lepton is going out. If the quark is coming in, the same quark is going out for this interaction. So it's the same L or Q. If it's a photon interaction like this. And what is the visualization? What is the interpretation of this? This is some fermion comes in and it emits a photon and keeps on going, right? So here comes my fermion coming in, and then bam, it shoots out a photon and then just continues on its way. So I would say this is called the emission of a photon. What's a big rule for it? It does not change the fermion. So if I have something drawn like this, if I have an electron coming in, so I'll do an example. Here's an electron, fires off a photon, well, that electron just keeps on going. Sorry for my wavy hand here, but here's the photon being emitted. So this is, let's say it's an electron in the orbit of an atom, it's excited state, it drops down to its ground state, and it shoots off a photon, gets rid of the excess energy. It's still an electron, it's just less energy. So it doesn't change the fermion when it emits the photon like this. And the other rule is no neutrinos. Neutrinos do not interact using the electromagnetic force. So no photon interaction with neutrinos. But the other fermions are fine. Electrons, muons, up quark, down quark, whatever. All right, next one. We could have something very similar. We could have, here comes some kind of a fermion coming in, and then now, instead of a photon being emitted, we have a weak particle, a weak boson being emitted. So for this one, let's say this is either W plus or minus, not a Z for now. These are one of the W's. Well, you could have some fermion. It could be neutrinos, any lepton or quark. Okay, so any of the fermions. I'll call it L1 or Q1, right? So some lepton, let's say an electron, or some quark, let's say a charm quark. It moves along, emits a W, so a weak interaction, and you get out of it some different fermion, so some L2 or Q2. Okay, and it emits this W in doing so. So this is emission of W boson. What do we know about it? Well, one thing we know is it changes the flavor of the fermion. So what does that mean? Well, for instance, let's say you had an electron. It could turn into a neutrino, an electron neutrino. Or you had a muon. It could turn into a muon neutrino. Or a tau. Guess what? Tau neutrino. Okay. So let's say this is an electron coming in. Here's an example, right? An electron coming in, shoots off a W of some sort, and what we get out is an electron neutrino. And now I'm going to go ahead and give the answer. What kind of W is this? But we'll see the rule later. This W would have to be a W minus. How do I know? Charge conservation says On the left side of this vertex, we look at the total charge, -1. On the right side of the vertex, we have to have the same charge. Well, the neutrino has no charge, so the W better have the -1. So it's a W negative. So there's an example of this changing the flavor of a fermion from an electron to a neutrino. If we're talking about quarks, it goes like this. Let's say you have an up quark. Well, that up quark can change into one of the other in its family. So an up can become a down, or an up can become a bottom, or a strange. So if you remember the table, we had up, down, charm, strange, top, bottom, right? So an up, if you start in the top row, a top row thing can become any one of the bottom row things. So it can become a down, strange, or a bottom. And of course the same for the down, right? The down, what can he do? Well, any bottom row thing can become a top row thing. So it can be an up, a charmed, or a top. And I could do this for all of them, right? A strange, he's a bottom row, so a strange can become an up, a charmed, or a top, and so forth. Now, this is called quark mixing. You're mixing up what flavor of quark or which member of the family. You're going from a top to a bottom row, or a bottom row to a top row. But some rules about this go like this. Because an up can change into any one of these three, they're not necessarily all equally probable. It's not necessarily true that an up can just as easily turn into a down as it can a strange. And in fact, it can't. It's harder to become a strange quark than a down quark if you're an up quark. And the way we see it goes like this. For quark mixing, which is what this is, the favored route is to stay in the family or the generation. Sometimes we call these families. This is first family, second family, third family, or generation. First generation, second generation, third generation. So when an up becomes a down, it's staying in its own family. If an up becomes a strange, it's crossing into a different generation. So for quark mixing, the most favored route is always to stay in the family. If you cross, a cross generation is suppressed. Suppressed meaning it's less probable. So when you work these probabilities, you could put some weighting on the different possibilities. So maybe when an up goes by this weak interaction, it could change into one of these three, down, strange, or bottom. Maybe 80% of the time it becomes a down, 15% of the time it becomes a strange, and 5% of the time it becomes a bottom, right? So if you cross generation, it's suppressed, it's less likely. Double cross, so going from up all the way to bottom, 3, the third generation, that's called doubly crossed. Well, it's doubly suppressed. It's even less likely. Okay. Big thing here, no horizontal mixing. So that is, an up cannot become a charmed. If you're in the top row, you become a bottom row guy. If you're in the bottom row, you become a top row guy. Okay, no horizontal mixing. So the rule for this guy, no neutrinos for electromagnetic interactions. Rule for this guy, no horizontal mixing of the quarks. And the same for the leptons. Okay, next, what do we have? What about the Z? We see a lot of these W's plus and W minus interaction. What about the Z? Sometimes the Z is called a neutral current, because this is the weak boson that is neutral. It doesn't have a charge like the W's do. So neutral current, what do we have? Well, it'll look something like this. You have some fermion. It could be any of the fermions. So L, Q, V, not V, neutrino. Here we have our Z. Here we have our L, Q, or nu. All right, so what do we know about this? It does not change the fermion. Okay, this is basically the same as photon emission, except neutrinos are allowed. Okay, so just like the photon, so just like the first interaction over here, some lepton emits a photon and keeps on going. Here, some fermion emits a Z and keeps on going. But now, neutrinos can partake in this interaction, whereas you never have a neutrino in the other interaction. Okay? So Z naught is just like a photon, but it allows all the particles instead of excluding the neutrino. Finally, the last one we have is for the gluon, for this right here. We've done the weak, we've done the electromagnetic, now we have the strong, and it goes like this. We have a quark. Strong interactions are only for quarks. A gluon is emitted, and quark over here. You say, well, wait, isn't this just like the photon and just like the neutral current, the Z, except this one only works for quarks, so only for quarks. So no leptons allowed. But it's not exactly the same. There is a change here. The quark type, the flavor of the quark, if it's an up, it stays an up. It doesn't change to a down. So we stay as the same flavor, but now what happens is you change color. Sometimes they call it color flavor or color charge. Change the color charge. So let's say you had a red up quark. Well, that red up quark can become a blue up quark, let's say, or something. It changes the color. And there are different gluons for different color changes. So you'll have, an anti-blue or anti-red blue, let's say, or something like this. Different colored gluons. They always come in two colors. And that's the guy that allows one colored quark to change into a different colored quark. Stays the same flavor, changes color. We won't be able to see it when I'm drawing these things. I'm not going to draw them in color. And for the most part, for now, we're not going to get too deep into chromodynamics. But we know quarks have this color charge. We know that if you have a baryon, a proton or a neutron, let's say, then the three quarks must combine such that they each have a different color, so you get a total neutral color, a color of white, let's say. So we know these things have colors, and the way they could change color is by the emission of these gluons. Okay? So that's what gluons do with quarks. Now what I want to do is go through some rules. So let's say you have something like this. We have an up quark, and we have the emission of a W, and that up quark becomes a down quark. Is this allowed? Well, let's look at the rule for the W's. An up quark, right here, an up quark can become a down quark with the emission of a W. Okay, so this is allowed. What kind of W is this? Is it W minus or W plus? Well, the up quark is positively charged, positive 2/3. The down quark is negatively charged, negative 1/3, so this better be a W positive. Okay, so that the left side has a positive 2/3 charge. The right side better also have a positive 2/3. Well, W plus is plus 1. D is minus 1/3, so 1 minus a third is positive 2/3. There we go. Now, what do we know about this? There's a rule that says if you move the placement of a particle in your diagram, so let's take this W and move it to the left. It's currently moving off to the right, so forward in time. Now we're going to have it, instead of it being emitted, we'll have a W being absorbed. So we'll do something like this. Let's say the up, still there. I didn't change him. I didn't change the down. Here's my up. Here's my down. But now all I did was I changed, make sure it looks dotted. I changed the location of the W. Instead of it being off to the right, it's now coming in from the left. The rule says if you move a particle's placement from right to left or vice versa, so right to left or left to right, it changes to its antiparticle. So, if this is true, this should, instead of it being a W plus, should be a W minus. Is this true? Does this work? Let's look at conservation of charge again. On the left side of the vertex, what's the total charge? I've got up, which is positive 2/3, and a W minus, which is minus 1. So 2/3 minus 1 is minus a third. On the right side, I've got a down quark, which is minus a third. Perfect. Charge works out. So this guy on the left, that's a W plus emission. That changes an up quark to a down quark. And on the right, we have a W minus absorption, which changes the up quark to a down quark. They're both fine. Well, what else can we do? Well, let's keep going. How about we now move, we take this second one. So I'm going to move him down here. I take that one, so the W is still over here on the left. Here he is. I'll just draw him straight instead of angled. And now the down is still here. But now I'm moving my up to the right side. So the up was on the left. Now he's going to be on the right. So how should this change? Well, the W minus is still a W minus. The D is still a D. I didn't change them. But because I changed the up from being on the left side to the right side, it needs to go to the anti-particle, which is an anti-up. And so I have to put the arrow the other way here. Okay, this is what's called pair creation. I had a W boson, a propagator, and this thing decayed and turned into anti-up down. So this is maybe some kind of pion or something like this, some meson. Remember, baryons have the 3 quarks. Mesons are a quark-anti-quark pair. So this is the K of a W to create some meson. Okay. What else? Well, how about if I were to have taken, let's say, the first guy there on the left, the very first vertex I drew, and I keep him the same, so my up still on the right, still on the left, sorry. The W is still on the right, so this is still a W plus, this is still an up. But now what I've done is I'm going to take this D, the down quark, and shift him from the right side to the left side. Okay, so now here's going to be my D, but because I moved him to the other side, he becomes an antiparticle. And so this is a new vertex, a new interaction. This is called pair annihilation. So pair creation, pair annihilation. Okay. So this is a nice little rule. If you have some vertex, some interaction, you can discover what other interactions are possible by moving the little lines around. knowing the rule that if you move the line from one side to the other, you have to change it to its antiparticle. Okay? All right, what's another rule? Well, how about this? Let's say you have some interaction. Let's say we have an up. There he is. And this is the emission of a W, right? So we have the W plus, and we get a down. So what I can do is do something like this. I can make a different interaction, very similar, which is every particle becomes its antiparticle. So that goes this way, that goes this way. And this is a legal interaction as well. So this rule says you can replace every particle with its antiparticle. And it's still a legal interaction. Okay? So that's another rule. First rule, given a vertex, you can move the lines around, move where the particles are located on the diagram. When you go from one side to the other, you change that particular particle to its antiparticle. Here, you could take an interaction, don't mess with any of the positions, but just change every particle to its antiparticle, and it's still a legal operation, still a legal interaction. Okay? Here's something else to know. Remember, what all these diagrams are leading us to is some mathematical description, some calculation we can do to figure out how likely is it for an interaction to occur. So maybe if I'm doing a particle physics experiment where I'm trying to create a Higgs boson or I'm trying to create a kaon or something, and I say, well, I know theoretically if I take these particular particles and I bang them together, it's possible for this kaon to be produced. However, what I'd like to know is, how likely is it? How many times do I have to run this experiment before I expect to get a valid result? Because you bang these particles together, there may be 1,000 different reactions that can occur. And the one you want is only one of that 1,000. But it's not 1 in 1,000 because each interaction has some likelihood. It might be that your particular interaction is extremely rare. Yes, it's 1 in 1,000 different options, but on top of that, your particular thing has a 1 in a billion chance to happen. So just because there may be 1,000 different things that could happen, that doesn't mean the chance of any of them happening is a 1 in 1,000. Instead, you have to look at how likely a particular thing is to occur, and here's some of the rules. The likelihood for something to occur is kind of based on the number of vertices. So what this means is if you have a particular diagram that has one vertex in it or two vertices in it, that's more likely than a different diagram that has 4 vertices or 8 vertices or 15 or 16 vertices or whatever. So the more vertices you have, the more of these little nodes here that are in your diagram you have, the less likely it is to occur. More vertices are less likely. And that's why, as I said in the previous video, even though there may be an infinite number of ways for a particular interaction to occur, because you could keep on building more and more little complexities into your base diagram, infinite number of times, we can still get valid answers by adding up this infinite number of times, because the probability of each time you make it more and more complex is going down and down. It's getting less and less likely. So it's like adding an infinite sum in calculus. As long as it drops off in a particular way, fast enough, it won't diverge. It'll converge to a particular number. So, more vertices in your diagram, less likely. Also, given an interaction, so if you notice, if you remember back here when I talked about the neutral current, I said this thing works just like the photon, or the gluon works very similar to how the photon and the Z works for a quark specifically. So let's say I have an up quark that's going to change into an up quark and emit a boson. Well, that could be done with a photon, it could be done with a Z naught, or it can be done with a gluon. Of course, the gluon is special because it also changes its color, whereas the other two don't. But let's put that aside. The question is, which one of those interactions is more likely to occur? Is it more likely that an up quark will emit a photon and remain an up quark, or emit a Z naught and remain an up quark? And the rule goes like this, and it's very nice. That's the naming convention of our forces makes this quite clear. Strong interactions are most likely. Then, electromagnetic interactions are less likely. Finally, weak interactions are the least likely. That's why they're called the weak interactions. Least likely. So the strong interactions are strong. One reason is because they're the most probable to occur for a particular interaction. The most probable route for this interaction to occur would be the strong force if it's allowed to use the strong force. So we're talking about quarks. But if we're talking about leptons, let's say, of course, an electron can't feel the strong force, so then it's between the electromagnetic or the weak. Well, the electromagnetic is going to be more likely to occur than the weak interaction would for the same results. So electron turns into an electron by emitting a photon, or electron turns into an electron by emitting a Z naught. The photon is the dominant one. The Z naught is way less likely. Thus, weak interaction. It doesn't occur that much. Okay. Conservation laws. Here's some conservation laws we're going to keep track of. Of course, there are more, but for the first round of this, to get the majority of stuff we need to worry about, these are the ones we're going to think about. First, of course, the big one is charge. Charge has to be conserved. What do we mean by that? That means when you look at a vertex, so some node, all the particles on the left, you add up all their charge. So the charge on the left must equal charge on the right. So again, we were just using this to figure out how these W's work. Let's say for this one here, I said, okay, I've got an electron turns into a neutrino and it emits a W in doing so. The question is, was it a W minus or a W plus? Well, if you're not given that, if you're the one who has to figure out which W it'll be, we use charge conservation. And remember I said, look at the node, everything on the left of the node. Well, there's only an electron. Charge of an electron, -1. Now look at the right side of the node. There's two things there. The neutrino, thankfully the neutrino has no charge, so he's 0. And then there's a W. Well, the W's charge better be equal to -1 so that the left side is equal to the right side. And so it must be a W minus. So that's charge conservation. Very basic, really easy to do, as long as you remember which particles are positive and negative. And usually the notation will show if it's a positive or negative. Like if you have a pion, is it a negatively charged pion or a positively charged pion? Because there's multiple versions. Unlike a proton, all protons are positive. That's not true of other particles. There are positive and negative, and I believe neutral pions as well. So usually what you'll see is something like pi minus. It tells you right there, it's a negative. But if we're talking about quarks, you need to remember, is the charm quark positive 2/3 or negative 1/3? Okay? And again, for that, it's easy to just think about, are you in the top row or the bottom row of that little chart for the generations? All right, so that's the first big one, charge conservation. Oops. Charge conservation. Next one, lepton number. This is a new thing we're not used to as a conservation law in physics, but this is true, a lepton number. And there's a little bit of complexity to it, but there's two versions of lepton number conservation. The first is the total lepton number. So what do we know about these leptons? Well, there's the electrons, there's the muons, and there's the tau. Each one of these has a lepton number of +1. The antiparticles, so the positron, the anti-muon, and the anti-tau, they have -1 lepton number. This is always true. If a particular particle has a quantum number, like charge, or baryon number, or lepton number, or flavor, or whatever, then its antiparticle has the opposite version of it. So for lepton number, the normal leptons, +1, the anti-leptons, -1, and the neutrinos, very similar. The neutrino has, for the electron neutrino, the muon neutrino, and the tau neutrino, they each have +1 lepton number, and the antineutrinos have -1 lepton number. Okay? So that's total lepton number. So you would look on the left side of a node. How many leptons do you have? Add up all the lepton numbers on the left side, and it better be equal to the total lepton number on the right side. Just like charge, except instead of charge, it's called lepton number. Okay? However, there's also each individual lepton number. So an electron and a muon and a tau, they each have a lepton number of +1. But there's also an electron lepton number and a muon lepton number. So, for instance, an electron and an electron neutrino have a electron number of +1, but the mu, the neutrino mu, the tau, and the neutrino tau have lepton number of 0, because they're not electrons. They're mu's or they're taus, so they don't have electron lepton number. And of course, anti-version is the same, right? E plus, and anti-E neutrino is a negative electron lepton number, and 0 for the anti-versions. Okay. So, and then there's not only the electron one, there's also the mu one, and there's also the tau one. So just like electrons and electron neutrinos has electron lepton number of +1, but the muon has electron lepton number of 0, well, the muon and the muon neutrino has a +1 muon lepton number, and the electron has a 0 muon lepton number. Obviously, it makes perfect sense. Once you know these are quantum numbers to worry about, following them along is not that big of a deal. You just count how many electrons are there. There's one electron, so it's +1 electron lepton number. On the right side, what do we have? How many electrons, or how many electron neutrinos? Okay, so there's the total and the flavored ones, or the generational ones, or the family ones. Total lepton number has to be conserved, and on top of that, the specific lepton numbers also have to be conserved. So you need to conserve both, or all of them, individually. Conserve the total, conserve the electron ones, conserve the mu ones, and conserve the tau ones. Each individually, all must be conserved for this conservation law to be true. All right. Baryon number. Just like for the lepton number, the baryon number is the same kind of a thing. Remember, baryons, those are the 3 quark people. So things like protons and neutrons. For the ones we care about, protons, +1, neutrons, +1, electrons, no. What about pi? Pion, pi plus, pi minus? No. Pions, these are mesons. Mesons, while they do have quarks, they're 2 quarks, a quark and an antiquark. Baryon number is only for 3 quarked particles. So it's not how many quarks are there on the left is equal to how many quarks are on the right, but how many baryons are there. Okay? So that's another one that needs to be conserved. If you have a proton on the left, and you do some kind of a weak interaction or strong interaction, whatever, and you have some other particles on the right side, you better still have a baryon on the right side. It may not have to be a proton, it could become a neutron. But if you have a 3 quark particle on the left, you better have a 3 quark particle on the right. So that's baryon number. Flavor. This one's an interesting one. Flavor is conserved in strong and electromagnetic interactions, but not weak interactions. So, what does this mean? Here's an example you may see. We have a kaon, K plus, turns into a pi plus and a pi 0. Okay, so what do I know about these things? Well, look at the charge. Charge is conserved. Charge on the left is equal to charge on the right. The pi 0 is neutral, pi plus is +1, kaon is +1. So charge conservation says no big deal, who cares? But I know this can happen because I happen to know the kaon has one of its quarks is a strange quark. But for the pions, there's no strange quarks. Right? Ups and downs, or anti-ups and downs, or things like that. So in order for this interaction to occur, this would have to be something like something that has a strange quark becomes an up quark. Now we saw way back here, right here, the strange quark can become an up quark, right? It can cross generations, there's no horizontal mixing, but the strange can become a charmed, the strange can become an up, the strange can become a top. You could change what kind of quark it is, the flavor of the quark, but these are weak interactions. Right? The W is emitted when this happens. But for photons and gluons, notice for the gluons, it only changes the color. For the photon, it just changes the energy. You don't change the flavor of the quarks. So, that's what this conservation law is saying. Unless it's a weak interaction. If it's a strong or electromagnetic, the types of quarks you have on the left are the same types you have on the right. Now, usually what this winds up being is like counting the strange number. How many strange quarks are there? That's why it was called strange. There was something when these particles that have this type of quark in it were discovered, they didn't follow the conservation laws the way we thought, because we didn't know flavor was a thing here, or at least flavor conservation. It's like, well, there's no reason. Why can't the strain, whatever this new quark is, it's kind of acting like a down quark, but it's heavier. Well, I know a down quark could become an up quark, so why can't this guy become an up quark? Well, it turns out it can't, because flavor is conserved. And so because it was acting weird, it was acting strange, they called it a strange quark, because that's the guy not allowing it to happen. So usually at this level, when we talk about flavor conservation, you're usually looking at, is the strange number on the left equal to the strange number on the right? But here's, unfortunately, the worst part of this. A strange quark is defined to have a strange number of -1, whereas an anti-strange is defined to have a strange number of +1. So it's the opposite of everything else, right? An electron has a +1 lepton number, a +1 electron lepton number, whereas the anti-electron, the positron, has -1 of those numbers. And it's the same for everything. But by convention, by definition from the beginning, the strange quark has a strange number of -1. So when you count the number of strange quarks on the left side of an interaction, those are negatives, not positives. So the kaon, if it has, let's say, one strange quark, then it would have a strange number of -1, not +1. So that's very, very unfortunate, but it's one of those things. Like current is defined as the direction protons would be moving through the wires, but in actuality, a current is literally electrons moving in the other direction. Here, the strange quark has a strange number of -1. The anti-strange has a +1. Okay? So those are the conservation laws we would need to worry about when looking at an interaction and telling, does this work or does this not work? Lastly, I'll go through kind of like a summary of what are the allowable interactions here. Okay, and this is what I mean. Let's say we're talking about electromagnetic interactions. You basically have two types. Now remember, when I say you have two types, you also include being able to move one of the lines from left to right by changing its antiparticle, or changing all the particles to the antiparticles. All those rules we talked about at the beginning still hold, but the two basic interactions would be a photon coming in, done, and then we have two fermions. We'll have one regular and one anti. So this could be, an electron and a positron. This would be pair production, right? An electron has a whole bunch of energy, a super amount of energy, and then it eventually collapses and creates an electron-positron pair. Or muon, anti-muon pair. Or a tau pair, anti-tau pair, right? So electron and positron, or muon, anti-muon, or tau, anti-tau. So those are the ones with the leptons. Of course, we could also do the same with the quarks. You could have a photon. Here's my photon. Quark, anti-quark pair. Same exact way. Up, anti-up. Down, anti-down. Charmed, strange, top, bottom. All the same. Charmed, strange, top, bottom, but all antis. Okay, so a photon can produce an up anti-up pair or a down anti-down pair. Okay, can the photon produce an up anti-down? right? Is that why can it go from up to anti-up? Can it go from up to anti-down? Well, no, because you also have to conserve charge. Remember, whenever we're dealing with these things, charge is conserved. So the charge on the left, photon, has no charge, 0. So the total charge on the right better be 0. But if it's up and anti-down, up has a positive charge of 2/3. Anti-down has a positive 1/3. So that's a total charge of +1 on the right. +1 on the right, 0 on the left, not allowed. So these are the two basic vertices for the electromagnetic interaction, for leptons and quarks. And of course, like I said, you could always move these arms to one side or the other and create new versions of these things. The weak. So for the weak, we could have something like this. You could have a W. I'll make this one the W minus. Okay? And that could become an electron and an electron antineutrino. So that would look like that. Or mu, muon antineutrino. And of course the same for the tau. Okay? So that's one. And then we could also do it for the quarks. We could have a W coming in, decays, becomes, let's say, a down and an anti-up. This would be, well, W minus here, I believe. This would be same generation or same family. So you could have down, anti-up, you could have strange, anti-charmed, or top, not top, bottom, sorry, bottom, anti-top. Right, so flavor, or quark mixing, but staying in the same generation. So down to up, but with an anti because of the way these are arranged, and conserving charge and all of that. So that's the favored one. This is the most likely. But you could also have cross generation. Okay, so W minus again. You could have a down. This is going to be anti this way. So you could have a down can go to a charmed, anti-charmed. Right? So from first generation to second generation. Or you could have the strange, that's a second generation, could go to anti-up. Or you could have a strange go to anti-top. Or you could have a bottom. The bottom can go to an anti-charmed. Right? So this is one cross generation. One cross generation. This is suppressed, so it's less likely. So favored, suppressed. And of course, we could do the doubly crossed. That would look something like this, W minus, production, normal, anti. So what can we have here? Well, we need to cross over two generations. So let's say we start with a down. We have to go all the way to third, which is top anti. Or we could start with a bottom, and that could go all the way to anti-up. But those are the only two, right? There's only two ways. There's only two. If we start with a down, of course, you could also do the same with the ups. You know, up goes to anti-bottom. I'm just giving a basic example. So we need to cross both generations, so you have to start at the ends. There's no middle stuff here. So this is two cross or doubly crossed. Doubly suppressed. So it's the least likely of them. Okay? Neutral current. Just like the photon one, the Z can do the same kind of thing. So Z naught, that's the neutral guy for the weak. And what can we have? Well, if you remember the photon, electron and positron, muon and anti-muon and so forth, same exact thing here. Electron, so these are the normals, these are the antis. Electron can become a positron. muon can become an anti-muon, and a tau can become an anti-tau. But now, the new thing with the Z is that the same can hold true for the neutrinos. So we could have a neutral current, regular, anti. You can have an electron neutrino becomes an electron anti-neutrino. A muon neutrino, anti-muon neutrino. Tau neutrino, anti-tau neutrino. Okay? And of course the quarks as well. So you can have the Z. Normal, anti, up, anti-up, down, anti-down, charm, strange, top, bottom. All the same stuff as before. Charm, strange, top, bottom, antis. Okay, so just like the photon, only now we're allowed to have this one as well. Okay, so those are all the weak ones. The electromagnetic, then we have the weaks with the W's and the Z's. And remember, like I said, you could do the same things, but with the other version, so up and anti-down, but then you may have to change to W plus instead of W minus. This is just your single layer, simplified, basic examples. Finally, we have the strong interactions. This is easy because there's only one you have to worry about. We have a gluon. Regular, anti. So here's our gluon. Up, anti-up. Down, charmed, strange, top, bottom. Down, charmed, strange, top, bottom with antis. So remember, the gluon, what it does is it changes one color to the other. So if we were to take this arm here and move it over here, you would have an up quark, because when you move it to the other side, you change its antiparticle. Up quark, taking in a gluon, and it changes to an up quark. It doesn't change the flavor, it only changes the color. So if you have an up, it becomes an up. If you have a down, it becomes a down. But if we draw it like this, so it's like a production of stuff, then if you have an up, it's an anti-up. Down, anti-down. The same generation. No quark mixing or anything like that. You're only changing color, and it's only for quarks. No leptons here. The last thing I want to show is this never happens. Never happens, and that is anything coming in, and we have a quark and a lepton like this. Anything. I don't care what this is. This never happens. So if you see something like this, and remember you can move the arms around, you know something's wrong. Okay. So that's kind of a cheat sheet, kind of like tips and tricks and the rules for Feynman diagrams. I know it's a lot of stuff, but really it's more like a few little rules and then just showing examples of what all the possibilities are, because there's lots of particles there. But each one is basic. For photons, you're just basically changing the energy, or you're producing two particles, a particle, antiparticle, or you're collapsing them, or whatever, but you're not changing the types of particles. So if you have an electron coming in, you got an electron going out. The only thing with the photon stuff, no neutrinos around. Weak interactions, there's several versions. You have to know W plus or minus, but that's from charge conservation. What do the weak stuff do? They change things. So if you have a weak interaction, an electron will become a neutrino. So a lepton becomes a neutrino. A muon becomes a muon neutrino, and so forth. For the quarks, you're changing the flavor of the quarks. An up can become a down, or an up can become a strange. You never have horizontal mixing, so an up cannot become a charmed. And you could either stay in your family, stay in your generation, so up to down or down to up, or charmed to strange, strange to charmed, and so forth. Or you could cross generation. So you're from up to strange. But if you cross your generation, it's less likely to happen. It's suppressed interaction. And then, even worse, if you try to cross over 2 generations, so from up down to bottom, or from top down to down, then it's doubly suppressed. It's even harder to happen. And then you've got the neutral current, the Z, but the Z acts exactly like a photon, only it allows neutrino stuff to happen. But it's exactly the way a photon works. If you have an electron, it stays as an electron. If you have a tau neutrino, it stays as a tau neutrino. And in the gluons, just like a photon as well, except it only works for quarks, no leptons anywhere, no neutrinos. But hidden behind the scenes is it is changing something. It's changing the color charge. So an up stays as an up, but a red may become a blue or an anti-blue or whatever we want it to do, depending on the gluon. Some other rules, you could change the placement of a particle in the diagram, but when you shift it from one side of a node to another, that changes it to an antiparticle version of what it was. So if it was an anti-down, it now becomes a regular down, and so forth. What else do we have? You can also take a diagram and for every one of the particles, replace them all with their antiparticles, and it's still a valid diagram, even if you didn't change anything else. So the placement stays the same, it's just you're changing every particle to its antiparticle. The likelihood of an interaction occurring? Well, all else being equal, strong interactions are primary, then electromagnetics are less likely than that, but still likely. The weak interactions are the least likely to occur when everything else is the same. So the diagram doesn't change, it's the same diagram. The weak interactions are the least likely, the strong interactions are the most likely if it's, allowable. And if you have a diagram, so maybe we have something like this. We have these two things, up, say anti-up, photon like this. And let's say that photon becomes up, anti-up. Okay, so what is this? This is pair annihilation. So an up and an anti-up come together, annihilate, and become a photon. Then that photon continues to go. So this is like you're putting 2 different vertices together, right? The first vertex here, and then you attach this other puzzle piece to it, and you become a bigger interaction. So up, anti-up, annihilate, become a photon. That photon eventually creates an up and an anti-up, pair creation. So annihilation, then creation. This is an interaction. It's got 2 vertices. I could also have something that looks like this. Same basic thing. Up, anti-up, up, anti-up. But now we can have a photon from here interact like this. So you can think of this as something like the up and an anti-up are coming along. The up sends a photon to the anti-up so that it feels a Coulomb force. It interacts by the Coulomb force here of attraction, pulling them together. And then they continue to go, and that's when they annihilate, become a pure photon. That photon then decays and becomes an up anti-up again. So almost identical, except in the second one, the 2 quarks are talking to each other. They send a photon between each other. When you look at this, there's 1, 2, 3, 4 vertices in this guy. Same particles, same basic interaction, but because we're allowing that extra thing to happen, this extra mediation, that's got 4 vertices. 4 vertices is more than 2, so this is less likely to happen than the first one. It still contributes, so when you actually calculate what is the scattering amplitude, or what is the likelihood of a pair creation or a pair annihilation and pair creation to occur for an up and an anti-up by the electromagnetic interaction. Well, you do the basic one, then you complicate it like this, and then you keep complicating it by adding more things. Again, I can also have pair creation happen in here, right? Up, anti-up happens, and then they come back together and become the photon again. That would have 6. 1, 2, 3, 4, 5, 6 vertices. So that's something that could also happen. So it contributes to the likelihood of the overall interaction of happening. It's just that this is way less likely. It's harder to do. So that's what this is talking about. The likelihood of an interaction to occur is based on the number of vertices in that diagram. The more vertices you have, the less likely that way of it happening is to occur. The simplest one is always the most favored and thus the most likely. But it is possible that these other ways can also happen. So you have to include those. So for instance, let's say as an example, we're flipping quarters. And I say, okay, what is the likelihood that you'll get 3 heads in a row? Well, you could have, heads, tails, heads, 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 tails, heads, tails, heads, whatever. But you could also have heads, tails, heads, 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 tails, heads. That's a different way for 3 heads to come up, but that's less likely because there's more heads to go along. But it's a way it can happen, even if it's less likely. So if you want the total probability to get it, you say, okay, I could get it this way, or I could get it this way, or I could get it this way. Each one has its own little probability associated with it, and you add them all up. And that's the total probability. Conservation laws, when you're looking to investigate whether something is a legitimate interaction, or if this is a test, and someone says, here's a Feynman diagram, is this a legal interaction? The way you can figure it out, or another way they can ask is, what are the missing particles? Should this be a W minus or a W plus? Should this be a photon? Whatever it is. You look at conservation laws. Charge has to be conserved. Lepton number has to be conserved. That's total lepton number and each flavor. So not only does the total lepton number have to be true, but the number of electrons and electron neutrinos has to be conserved on each. And the number of muons and muon neutrinos and so forth. Again, antiparticles have the inverse of the regular particles version of these numbers, but that's fine. Baryon number, the number of particles that have 3 quarks in them. So like a proton has a positive 1 baryon number. A neutron has a positive 1 baryon number. Electrons, muons, taus, they're not baryons, they're leptons, so 0. Mesons, like the pion, they're 0 baryon number, even though they're made of quarks. So you're not counting the number of quarks, you're counting the number of baryons. And then flavor conservation, for our purposes, basically how many strange quarks are there. The problem with this guy, and that's why it's in red here, is it's the opposite of what you think. Strange quarks have -1 flavor number, or strange number, and the anti-strange quarks has +1 strange number. But once you know that, fine, whatever. You look on the left side of an interaction, how many strange quarks are there? And anti-strange quarks, add them up. On the right side, how many strange quarks are there? Add them up. And then left must equal right, just like charge. Those are conservation laws. And then, of course, I had some examples here of the allowable vertices, the base vertices you can have. And then you can mess with them, put them together like puzzle pieces, move an arm from one side to another, whatever happens. Okay? So I hope this is helpful. I hope it makes investigating these diagrams a little bit easier. Once you get used to the rules, once you know the weak interaction is the one that changes all the flavor types, whereas electromagnetic and strong don't, then it makes these things a little bit easier to understand. So anyway, if you have any questions, let me know, and I will see you next time.